Okay, we are back, and we're going to try to finish this topic here today. So, this is where we left. If you have any questions, just post them on the chat there, and I'll get to them in a few moments. Um, okay, so the question was, what is the proof that at the atomic level, matter can behave as a wave? We know that if it does, we're not going to see it in the macro world, as we saw with the example of the ping pong ball. But the key to answer the question came from another property of waves that we haven't discussed yet, and it's a phenomenon that is called wave diffraction. Wave diffraction. If you look at a beach like this one, where a wave breaker has been built, you can see that as the waves come in from the outside, from the ocean, and they go through this narrow opening, you can see where the originally, what do you call that, linear wave suddenly becomes like a radial one. It's like as the wave comes to a small opening, it kind of bends, so to speak, into these radial or semicircular kinds of waves. Well, light does the same thing. Here's a little illustration. Let's say that I have beams of light going from left to right, and the vertical lines here represent the crests of these waves that are coming in parallel. And you can see the distance between them as the wavelength, lambda, on the bottom. And let's say they hit a barrier. But in the barrier are two small slits. And those openings are about the same size as the wavelength. So as you can see, when the light beams hit those slits, they undergo what we call diffraction. In other words, they kind of bend through those slits and generate a series of semicircular, right, or radiating waves, all right? But notice that each slit generates a separate set of waves. And those waves are going to essentially encounter each other as they travel out radially. Notice that at some points, these waves are going to undergo a process called interference. If you look at the top picture here on the right, notice what happened there is that when the waves met, they were out of phase. So it was like crest to trough, crest to trough. And so essentially what they do is they cancel each other out. Now, because this was originally a wave of light, by having a flat line, that means there's no light there. And if you put a film in front there, you're going to get these dark bands in here. And that is what we call destructive interference. If, on the other hand, the waves meet each other in phase, and you can see the bright little points here in this diagram, you see several bright points in there. That means that the waves are meeting, crest to crest and trough to trough, which means that they add up to each other and they generate a wave of bigger amplitude. And that translates into these light colored bands in the film. This is what we call constructive interference. So in other words, if I run a beam of particles, like it's in the bottom here, through a slit in a wall, what's going to happen is most of the particles are essentially going to kind of like bounce off. Some of them are going to make it through. Now, they're going to make as linear. Some of them are going to collide with the edges here and kind of like get deviated. But if I were to put, let's say, a film here or a detector, what I'm going to see essentially is I'm going to see like a band there kind of in the middle, kind of smear where all the particles that made it through the slit actually hit. But if instead of a particle beam, what I have is waves, and I put over here a detector, what I should see is the typical banding pattern of wave diffraction. So what you guys remember J.J. Thomson, who was the guy who proposed the model of the atom, right? So basically his son, G.P. Thomson, and other guys did this experiment. What they did was they took a beam of electrons They ran it through a kind of like a barrier that had two slits in it, and they looked at the pattern that you found on the other side. The idea was that if the electrons behave like particles, what you should get is two bright spots or kind of bands on the target or on the detector or film. But if the electrons behave like waves, what should happen is you should see an interference pattern. In other words, you should see the banding pattern that you get from waves diffracting when they go through a system of two slits. Well, guess what they found? That's what they found. That was the experiment that showed that electrons do behave as waves when they're exposed to the right environment. But there was one problem with the experiment. What they wanted to do was they wanted to see, well, what does this look like? What is the electron actually doing? What does the electron look like? So what they try to do was they try to put some other detector here at the slit, right? So they could see what exactly was going through, and what was going on. What does the electron look like as it passed through that slit? And when they did that, the pattern they obtained was, again, the particle pattern. They no longer could see the wave pattern. It's as though the attempt to observe the electrons as they travel through these slits changed their behavior back into particle behavior. So that was a very, very daunting observation to explain until along came Heisenberg. Yes, no, not that Heisenberg. Werner Heisenberg, who proposed the following. What he said was that, let's say that I have an electron going in a certain path. Anytime I try to observe it, essentially what I'm doing is I am putting a photon in there. And just like in the photoelectric effect that Einstein had explained, the photon actually knocks the electron off course. It changes its momentum, and therefore, at this point, it no longer behaves as a wave. It's behaving as a particle that got knocked off course. Now, the photon itself also gets scattered, and so you have no possible way of actually observing this electron as it travels there, right? So what Heisenberg got out of this was the following. Not only does it tell me that I cannot observe the electron behaving as a wave, it tells me that I can do one or the other. I can observe the effects of the wave behavior of an electron, such as the interference pattern that we saw, or I can observe the effects of the particle behavior of an electron, such as, for example, in an electrical current, but I cannot observe both at the same time. So both the wave properties, which were proven by the experiment, and the particle properties, which were known from classical physics, exist, but they cannot be observed at the same time. And this is one way of looking at what is called Heisenberg's uncertainty principle. And what I have here is an equation that shows it. Now, guys, I don't need you to know this equation, and you might get a problem question in your homework where they have you do calculations with it. I don't need you to do that. I just want you to know what this means. So basically, in this equation, delta x would be the uncertainty in the position of a particle, and delta v would be the uncertainty in the velocity of the particle. Remember that we said that in these arrangements, for the wave properties of electrons, we basically assume that the velocity is determined by the wavelength or something like that. But it's usually going to have to do with the wavelength and the mass of the electron. M is the mass in kilograms, and H is, again, Planck's constant, adjusted in units to kilograms times meters squared per second. All right. So essentially, if we look at it just from a simple ratio thing, notice what this is telling me is that the uncertainty in the position is let me see if I can write here, is inversely related to the uncertainty in the velocity. So in other words, If I wanted to narrow down the position of the electron, kind of like pinpoint its location, kind of the way I do when I do a stop motion video of a baseball being thrown by a pitcher, and I can see, I can track its path all the way through every step of the way. If I wanted to do that with an electron, what's going to happen is I am going to generate a tremendous uncertainty in its velocity, essentially in its wave-like properties. If, on the other hand, I try to decrease, to minimize that uncertainty in the velocity, in other words, in the wave properties of the electron, I'm going to lose all kinds of certainty with respect to the electron's position. So the point here by Heisenberg was that, going back to the Bohr model, the reason why it doesn't work is because it is proposing that electrons are traveling in these very well-defined orbits, right? And although it is true that they have discrete values of energy, you cannot do what you do with planets in the solar system, where you can actually predict where each planet is going to be on this day of this month of this year, because the electron is not circling around the nucleus. The electron is not like a planet orbiting the sun. The electron does not have a fixed position. The electron is simply an oscillating charge/mass thing that's somewhere in there within the confines of that atom, and we can never exactly pinpoint either its position or its path. And any model that pretends to pinpoint any one of those values for the electron is going to fail because of Heisenberg's uncertainty principle. All right? Cool. So I'm going to leave it there, because what's going to happen next is that this guy, Erwin Schrödinger, was going to come up with a way of solving all this dilemma. All right? So I'm going to pause it here. Come back over here, and let me see if anybody has any questions. I know we are kind of like going some, mind-blowing stuff in here, but that is exactly what quantum mechanics was all about. All right.